Hello, everyone. Thanks for coming, and thanks, Luca, for hosting. So, I'm Sumit. I work in Facebook New York in the AI research department, and I'd like to know a little bit about the audience. So, how many of you are in research? A lot of researchers. Great. And how many of you are employees in data science or related robotics? Okay. Well, only one person is employed. Okay. Oh, a few people there as well. Great. Let's get started. So I'll be talking about PyTorch today. So this is the team of people who wrote PyTorch. Adam Pashka, the first author, he will be talking about hands-on PyTorch next. And the rest of the team, they've all contributed to make this happen. So I will be, because there's a lot of researchers in the room, and Luca did tell me that the primary interest is from researchers. I prepared a talk with you guys in mind. So starting with what is PyTorch. So PyTorch is several things. It's a library. It's a Python library that, and at the very base, you can see it as a replacement for NumPy with GPU support. So you can use it just like you use NumPy, or if you're familiar with MATLAB, you can use it like you use MATLAB, interactively create matrices and do linear algebra operations on them. But that's the base core package. And then we also have other packages to build neural networks. The main packages we have, or one is this automatic differentiation engine. And then we have neural network helper libraries and optimization packages to do common gradient descent optimization algorithms. So I'll be going over each of those. So starting with PyTorch's basic library, we have an ND-array library. It's very similar, as I said, to NumPy. We have 200 plus operations. Every operation you can accelerate on NVIDIA GPUs using CUDA, and it's you can, if you're a linear algebra person, you can do all the standard LAPACK functions like matrix inversions and SVDs and so on. And you can do standard slicing of matrices and so on. So to show you how similar PyTorch is to NumPy, here's a program. The left side is written in NumPy and the right side is written in PyTorch. I didn't put this slide up so that you can read the code. It's more like, okay, side by side you have like exact API, very similar API between PyTorch and NumPy. You can replace one with another. So the way you would use PyTorch is you would import the torch package, and then you can do standard things like creating a tensor. You can print the tensor, and you can construct random matrices. We have a lot of functions to generate random numbers, both on CPU and CUDA. You can do standard indexing, like slicing, getting particular elements, doing advanced indexing, and you can do standard operations, whether they're Pythonic operations or you can do matrix multiplies and so on. One of the things that's a cool feature once you're starting to get into PyTorch is PyTorch itself is one package, and we just released it in January, so our ecosystem is slightly small, but NumPy has been around for many years, and the general ecosystem of NumPy is very large. You have SciPy, you have scikit-learn, you have all of these things. So we provide a way to convert a PyTorch tensor to a NumPy array very easily. Like you just call .numpy on your PyTorch tensor and you get a NumPy array, and it's extremely efficient. This operation is almost like it's a free. You don't have any memory copy, so generally you can use this operation at will on CPU tensors. And one of the things, like what makes it extremely efficient and also something that's practically interesting is once you convert a PyTorch tensor to a NumPy array, you get, let's say A is your PyTorch tensor and B is your NumPy array. If you change anything in the tensor, the change will be also reflected in the NumPy array. So you don't need to constantly back and forth keep converting your tensor to a NumPy array. So as you see here as an example, A was constructed as all ones right here, and then it was converted to an array B, and then now I added 1 to A, and then I print A and B is also 2 now. So similarly, you can convert a NumPy array to a PyTorch tensor that also has like this 0 memory copy, extremely efficient approach. There's a function called torch.fromNumpy that will let you do this conversion. So we also have GPU tensors. So if you have CUDA on your machine, that is like if you have an NVIDIA graphics card that supports CUDA, then on any of the tensors that you have constructed, you can call .CUDA, and then the memory of the tensor is then transferred over to the GPU, and then if you do any operations on this resulting object, you will have these operations be done on the GPU itself. So it's typically much faster than if you do the same operation on the CPU. So coming to our automatic differentiation engine, so I'll take you through what it is in a quick example. So we have one package called torch.autograd. So this package implements all the operations that torch tensors implement, but you can take the derivatives of one operation with respect to another. So as a small example, let's say you have initial tensors W, H, and WX and X. So we have a class called variable that is a loose wrapper around a tensor, and if you create a variable and then you do any operations on it, then these operations can be differentiable. So here I create some random tensors, and then I wrap them in autograd variables, and then I'm going to do some operations. I'm going to do a couple of matrix multiplies between both of these operations. And as I do any operations on my variables, the resulting tensors will also be of variable class, and they will record how they were created. So for example, I2H here is a variable that wraps a tensor that's a result of this matrix multiply. And I2H remembers that it was created by a matrix multiply between W and H. So because you remember this history, then you can backprop through. So let's do some more operations. Let's add up these nodes. So NextH now remembers that it was the result of an addition between I2H and H2H. And then I'll take a tanH operation. And then on my final variable, I can call backward with some gradient with respect to the output. And my gradients will be accumulated into each of these leaf variables that were created. So x.grad will now include the gradient with respect to NextH. So it will be like the derivative of NextH with respect to derivative with respect to W. And so this is the differential engine that's pretty powerful, and you can create neural networks using this engine. Coming to neural networks, to show a small practical example on how you actually use the autograd engine to create things like convolutional neural networks and so on, we have a small package that is built on top of the autograd engine called NN. So it's called torch.nn. And the way NN works is it's just a convenience wrapper for all of our deep learning layers that you want to implement. So in NN, if you want to create a neural network, then you subclass a small class from nn.module, and that will be your neural network. That Python class will be how you define your neural network. And in the constructor of the class, you can define all of the layers that you would typically use in neural networks. For example, I define a convolution layer here, and I define a linear layer here, and so on. And these layers, they not only just define what operation you're doing, but they also contain the parameters, the learnable parameters of this particular layer. So self.conv1 here is a layer of type conv2d, and it has two important properties. Self.conv1.weight will be the kernels of your convolution that you will learn, and self.conv1.bias will be the biases that you will learn in the affine transform. And coming to the forward function, you define one function additionally apart from the constructor, which is the forward function. And this function, you define a Python program that goes from the input to the output. So in forward, you have an input that is your maybe it's an image or some video or text. You take the input, and then you just write out how the input will go to the output. Over here, the input is x, and then I first pass it through the convolution layer here, and then I pass it through max pooling, and then I get some result, and then I further process it through another convolution max pooling, and I also add some dropout here. Then I reshape the tensor to a flattened 1D tensor, and then I send it to the fully connected layer where there's a standard affine transform that is performed, and I apply some more dropout, and then finally I compute log probabilities of the output, and then that's kind of how your neural network is defined. And this forward function can contain any Python. There's no limitation to what you do here. And that Python code itself will define how your neural network is structured itself. And once you define your class, you can then instantiate your class. Like here, I instantiated the class. And then you can send some input through your model, and then you will get your output. And then you can call .backward on your output, and then that will compute the gradients. So coming to the optimization package, which is the next relevant thing. So once you create a neural network, you define your neural network, but then you want to train your neural network using some gradient descent algorithm like SGD or ADAM or all of these algorithms. So we have a small package called torch.optim that defines all of these ways of algorithms of training neural networks. And so the way you work is you create a network, an instantiation of your class, and then you create an optimizer. Here I'm creating an SGD optimizer, and to the optimizer you pass all of the learnable weights of your neural network, and then you can give additional options like learning rate and momentum and so on. And then when you want to actually train your neural network, you will loop over your data set, like some input and some target variable. And you'll first zero the gradients in the optimizer. That's just, in PyTorch, all of the gradients are always accumulated. So if you call .backward, it always doesn't override the gradients that are already there in some variables. It accumulates gradients into them. So when you're training a new sample, you want to zero the gradients. So you zero the gradients here, and then you compute the output of your neural network, and then you compute some loss function, because there's a room of researchers, I don't need to explain that. And then you take the gradient with respect to your loss, and then you will get the derivative dl by dx, where x is some neuron in your neural network that you want to train. And then what will happen is every variable that is registered as a parameter in your neural network, it will have a dot data, which is just the contents of the current values of your weights, and then you'll have a dot grad that will contain the gradients that you just computed with the backward. And then the optimizer, when you call optimizer.step, it will perform the update rule between some weight.data and weight.grad. So it will do weight.data minus learning weight times weight.grad in like the simplest case. If you have momentum or RMS prop, and these, like the update rule gets slightly more and more complicated. So that's kind of the workflow using the Optim and NN packages. Now coming to research workflows. Like now, I gave a brief overview of PyTorch itself. Now I am going to try to tell you how it might be useful in research workflows. So I'll just briefly summarize how research workflows look like and how PyTorch can help you dealing with each of these workflows. And then I'll discuss some recently implemented features and some upcoming features. So coming to research workflows. So let's say you have some idea. You're sitting in the lab and you're like, oh, I have this idea, I want to implement it. Or you come up with some theory, like you want to construct experiments to validate it. Or maybe your advisor has an idea and they said, okay, come implement this. Then you design some experiments. You're like, okay, I'll pick this particular data set and I'll construct my neural network in this way. And then I will train it. And if it gets to this particular place, then my idea is good and I will publish it. If not, I'll just write a blog post about it. And then you implement your models, you do some training, validation, and then finally, yeah, it comes to your paper. So this, and some literature review as well. So because professors are watching you, that's sort of important. It's not being done too much these days, but so this is, I hope, typically what research workflows look like, and it doesn't fit everyone's typical workflow, but I think it captures things pretty well. So in practice, now you have that workflow. In practice, how does this look like in terms of actual tasks? One of the crappiest, like horrible tasks to do is like, once you pick a data set, then you have to write some way of loading the data set and pre-processing it and normalizing it. And this is just like, it's probably gonna move like the largest part of your experimentation. And then you build your models, you define a neural network. Maybe if you're a vision person, you just say, okay, I want to build a ResNet or some GoogleNet or something. And then you implement some training, some scripts for that, and save models to disk and load them back and all of that. And then you build some baseline models. You're like, oh, I need to compare my method to some other previous method, so I'll build some baselines. And then if you're using neural networks, you're almost definitely dealing with GPUs to train them faster. And if yours is not a typical data set, let's say you're doing some video game learning or something, then you have to, or some robotics, then you have to do some real-time interfacing with that environment as well. So PyTorch combined with Python is one environment to do this. It provides all the tooling for you to achieve all of these tasks. And I'll go into how it might be. So writing data loaders. So as I said, every data set is weirdly formatted, and then you have to normalize it properly, otherwise your model doesn't learn. And then if you have a huge data set that's like terabytes of data, then you can't load it all into RAM. So you need to write some kind of put all the data sets in hard disk and then efficiently load them onto your RAM. and then onto the GPU, and then you can train your neural network. So some kind of multi-threaded data loader is needed. And with PyTorch, what we did was, for the most common cases like vision and text, we have democratized writing these data loaders. So everyone writes their data loaders, they share them with the community in the Torch Vision and Torch Text packages. If you write a data loader for some new data set, you just open a pull request, and then everyone else in the community benefits from this. They don't have to spend time writing a data loader for the same data set. And that's very helpful. And if you're using some common data sets for research like ImageNet or Coco or all of these, like we already have data loaders that people have written, and this list is ever growing. I think this list is already outdated. We have like quite a few more now, and that's one nice thing. And similarly, in the we have a text package. If you're doing NLP research, then we have a lot of data loaders in the text package to load standard data sets there. But apart from these, PyTorch itself is just a Python package, right? So if your data set has a Python API, then it's already like loadable in PyTorch. As an example, at Facebook, we recently released a package called Parlay. It is a small framework to do question answering tasks and various NLP tasks around question answering, and so that particular repository is a Python repo. It's not PyTorch specific, and it just provides 20 data loaders for various different data sets, and you can easily just use Parlay to write PyTorch use Parlay when you're writing your PyTorch code itself. So code in practice. How does it look? So if you're leveraging one of our existing data loaders, then typically, so this small snippet of code that I took from one of the examples is the option to load 3 different data sets. And each of them, as you see, are kind of similar. What you do is you create the data set. So we have an abstraction called data set, and we have an abstraction called data loader. So data loader takes a data set and makes it multi-threaded and computes them in parallel. So data sets are just like, okay, I want to load one particular type of data set, and so I'll write an API for it. So we create a data set, and then in the data set you give like path to where your data set is, and then for the vision data sets you can give these things called transforms that describe how you do pre-processing of your input images, and that typically happens. These are like all of the common transforms that you would do. They're already in the vision package, and then if you see here in lines 83 and 84, the last 2 lines, we create a data loader itself from the data set, and we specify how many workers, that is how many CPU threads you want to use to parallelly load up these data sets and pre-process them. You can specify things like batch size and whether you want to shuffle your data set or not. And writing your data sets itself is also quite simple in terms of API. If you want to create a new data set, you just subclass from torch.utils.dataset, and you define 2 functions. One is getItem. GetItem takes in some index. So typically if you have a data set, you have some, let's say you have million samples in your data set. So you can index your data set from 0 to like 999,999. So that index is just like which sample in your data set that you want to load. So you define a getItem with some index, and inside your getItem you can write some Python code on how to load that particular instance of your that particular sample from your data set and return it. And the second function you need to define is the length operator that just defines how many samples you have in your data set. If you define these 2 functions, and you can and then just instantiate data sets. That's pretty much it. Like, the API is fairly short and simple, and this is an example of using loading the Cocoa dataset. So Cocoa already has a Python API to load Cocoa images and objects and so on. So in your get item, we just load that particular instance of the Cocoa image along with its annotations, and then we just transform the images optionally, and then we just return the images and the annotations. That's about it. Interfacing with environments that are not, typical data sets. So if you have something like video games or something like OpenAI Universe, then almost like as of today, almost every one of these has a Python API. Python has become like a very standard tool these days. So if you have a Python API for your environment, then you can already automatically use it in PyTorch. So coming to debugging. So debugging is one of the other big nightmares when you're doing research. It's like, okay, my code is not working. What do I do? So you add print statements, you use debuggers. Because PyTorch is just a Python extension, you can naturally use it as you would use as you would debug any Python code. Python has several debuggers that come shipped with it. It has like a default PDB, but it also has like all these fancy debuggers where you can set breakpoints and stop and so on. So all of those you can use with PyTorch. There's nothing different from debugging PyTorch code than debugging Python code, and that's, I think, pretty powerful. So I come from a Lua land, so we wrote the previous version of PyTorch was called Torch, and it was written on Lua, and there's no tooling for Lua at all. So for me, coming to Python was like, oh my god, you have like a debugger. Oh, like all of these nice things. So yeah, I'm always happy with Python, and I think if you want to do anything in Python, you can just Google for a package for that, and it'll be there. So another thing is PyTorch is an imperative language. That is, every line of code gets executed immediately, and there's unlike TensorFlow or Theano or Caffe, it's not a declarative language, which means you can use the native, you can use the fact that as you write your code, it's being executed linearly. So you can add things like print statements, and it's completely fine. The ordering of statements is preserved. Another thing is you write your research code, it's a big pile of mess, and then you're like, okay, my deadline is approaching, I need to make it faster. So again, you can use any Python profiler you want for this. There's many good ones. There's some fancy ones like Snakewiz that will take your default Python C profile and visualize it nicely. There's something called Line Profiler, which line by line it'll tell you which of your lines is the most heaviest line. And if you come from a MATLAB world, then you have in MATLAB something inbuilt like this as well. The other thing is, as a researcher, you're always impatient. You're like the most demanding customer there is, but you don't have money, so open source software is best. So PyTorch is written for people who are impatient, who are researchers. I am a researcher myself, and a lot of people in our team are researchers or former researchers. So we understand and know how all of us work, and so we wrote PyTorch to have no compilation time whatsoever. Like if you take some Python script and run it that has PyTorch, then you don't wait for some some just-in-time, oh, we'll just invoke GCC on this code and compile. Like none of that business is there, unlike some of the other frameworks. So the downside of this, because we pre-compile everything, the download of the PyTorch package is quite large. So it's like 400 MB or so. So because we pre-compile everything and we do all of this business so that you avoid having to wait at runtime, our binaries are large, and that's just what it is. The other thing, as I mentioned, because PyTorch is a Python package, you can use the entire ecosystem. In PyTorch neural networks, you can intersperse SciPy, for example, and we have a tutorial on how to do that as well. As one of the crazy things I saw was there's this PhD student from CMU. He was writing PyTorch based neural networks, but then he was doing like standard traditional convex non-convex optimization, and this is like a primal dual interior point method optimization, and doing something like this in any other framework, according to him, is almost impossible. And so if you have crazy ideas, and you do have crazy ideas as researchers, unless you're a master's student, then you are definitely going to love how flexible PyTorch is. And if it's not, let us know, and we'll make it to be as flexible as your idea needs it to be. So as I said, we already have a small tutorial on how to create PyTorch extensions that use SciPy and NumPy that was authored by Adam Pashka. And the other thing we have is we have a shared model zoo. So if a lot of research these days is like, oh, we're going to start from this pre-trained neural network model, and then we're going to do some transfer learning, or we'll build on top of that to do some other task. And we have shared models across the community. As a small example, here's some state-of-the-art ResNet from the Torch Fusion package. If you want the pre-trained weights, that is like the ResNet with already like trained on ImageNet, then you simply give a keyword argument pre-trained equals true, and then the weights are automatically downloaded from our S3 buckets, and then they are loaded into your Python process and initialized. So it's like a one-touch argument that will automatically get you your latest model that you care about. And one cool thing you can do, one of the cool things that one of our community members did was he took all of the pre-trained models available in PyTorch, and then he was like, okay, how much does quantization affect neural network accuracy? So neural networks are typically trained in 32-bit precision. But he was like, okay, let me try to reduce the precision. Let me make it 12-bit neural networks, 10-bit, 8-bit, 6-bit. And once I quantize each of these neural network, especially the weights, to these values, how much accuracy would I get on my data sets? And I think it's pretty interesting that even at 8 bits, you don't have much loss in accuracy overall. The one of the last things I want to talk about is, again, PyTorch is what we call an imperative deep learning framework. There's two kinds, declarative and imperative. Declarative is where you declare your model beforehand, and then you execute it somewhere. Imperative is that forward function that I described for your neural network. You can just put any Python program in that forward function, and it just gets executed in Python line by line. So because PyTorch is an imperative framework, you have linear code flow. That is, if you're reading your code as well, like, you don't have to jump around 3 files on how something is getting executed. And similarly for debugging as well, you can stop in the debugger, inspect variables, and this is something imperative frameworks do provide, and PyTorch is one of them. And again, as I said, PyTorch is not the only imperative framework. There's other imperative frameworks as well. But one of the things we try to always push forward is PyTorch. We don't want to lose performance, that is the speed of computation, to any other framework. So we made sure PyTorch is one of the fastest imperative frameworks out there. And we're making it faster and faster. We have a lot of work going on to make it faster. So some of the recent and upcoming features, some of the features that we recently released and some of them that will come in the next few releases, I want to talk about. This is the last section of my talk. One is distributed PyTorch. In the last release 0.2, we introduced PyTorch distributed, where if by chance you have hundreds of machines, or 2 or 3 machines, and you want to train a single model on each of these machines, then we have an API called torch.distributed. It's an MPI style API, which means we have some functions that you run that can exchange tensors between each other. For example, they can sum up all the tensors amongst each other, or send one tensor from one node to another, and so on. Another feature we added recently is higher order gradients. Typically, until last year, Theano was one of the only frameworks which could do higher order gradients because of a symbolic framework. Now, several new frameworks support higher order gradients. TensorFlow, Theano, and PyTorch now. And this is typically useful if your idea is really crazy. If you want to, say, for example, penalize the diagonal of the Hessian or something, which you might want to do, or you want to use curvature information to accelerate your training, all of these things you can do, or you want to do meta learning. I want some gradients of my process simulated by another neural network. That itself will be some weird ideas, I don't know, but all of these things you can do with PyTorch now. We also introduced NumPy features like broadcasting and advanced indexing. If you know what these features are, then you already know that this is kind of nice. If you don't know what these features are, don't worry. We have another trick coming up, a small package that introduces just-in-time compilation for PyTorch. And this is not really what you think about when you run GCC on some big program and you're waiting for 5 minutes. This is, you don't notice any difference in terms of user experience while we're doing this JIT compilation. But in the background, we might be making your program much faster. And let me show it to you with an example. So typically, why do we need something like a just-in-time compiler? Let's say you write a small statement in PyTorch or in NumPy, like d equals a plus b times c. Now, because PyTorch and NumPy, these tensor libraries, they come pre-compiled with all these kernels, what will actually happen is you will first compute a plus b and put it in some output buffer, and then you will compute c times that output buffer. And if you are traditional computer scientists, you would know that almost all programs, the main bottleneck, if you have a lot of memory accesses, is memory. System memory is much slower than registers or L1 or L2 caches. So it's the same for GPUs as well. GPU main memory is much slower than GPU registers and so on. So if you want to make your program faster, so because tensors typically are 100,000 elements, or they're very large, you can't fit these things in L1 or L2 caches completely. So you are bottlenecked in this particular statement by how fast you can pump these tensors into registers, do your computation, and then pump them out. So we call these typical cases bandwidth-bound operations. So most of your deep learning workloads are bandwidth-bound. Probably all of them are bandwidth-bound, unless you only have a convolution going on in your without any other operations. Typically, all of the operations like ReLU, softmax, pooling, like all of these things are bandwidth-bound operations. So one way to transform this code to make it more compute-bound is by switching it to not really write back to main memory, but just do more operations in register. And this is just this type of optimization is called fusion, like operator fusion or code fusion. And this is very typical if you are compiling your code with GCC or something, it will try to do basic fusions. And if you are using PyTorch right now, you don't have this, or like if you're using NumPy right now, like you don't have capabilities like fusion because there's no concept of a compiler, because, you know, as I said, we didn't want to introduce compilation time itself. So some of the benefits are of having a compiler is fusion. Like one of the other ones is you can change the order of execution of certain operations with guarantees that the result is the same, but they're typically faster. Another one is, let's say you have some CPUs, some GPUs, you have a lot of computation. The compiler can decide, oh, I have like this other GPU free, I'll just automatically place some work on this one, and so on. We introduced into PyTorch recently, it'll be part of the next release maybe, what we call a tracing just-in-time compiler. What it does is it takes, let's say you have a small PyTorch program that computes, the addition of x and then multiplies it by 2. We add a small annotation on the function called torch.jit. I think we dropped trace, or I don't remember the exact syntax, but because it's experimental, it keeps changing. But you add a small annotation on the function, and then when you compute the function for the first time, our just-in-time compiler, it will trace through all of the tensor operations in the function. Once you execute, y1 equals foo of x, it will go there, and then it will see, oh, you took the input and then you added a 1 to it, okay, and then you took the result and then did a multiplication and returned it. So it will record this trace in some C++ data structure, and then it will try to do some optimizations on this trace in the background. And then when you run this function again with some other input, and that input's size and shape matches the first one, then it'll be like, oh, I've seen exactly what operations are done in this case. So instead of using the actual Python function, I will use the trace itself. And the trace was probably optimized by now with various techniques. And so it will actually run the trace and give you a result. So for the computer compiler nerds, we have an intermediate representation with tensors as fundamental types, and the JIT is optimized to have reusable traces, and when you're building tensor compilers, it's slightly different from building, say, JavaScript compilers, for example. One of the small gotchas at this stage is that our traces can't handle control flow. So you would only want to compile functions which don't have control flow, that don't have something like if conditions and so on. That's my last slide, and I want to just tell you that we released in January. We already have lots of people using PyTorch, which also means that communities are always, the bigger the community, the nicer it is to use the tool, and our community is growing. We have a nice forum that Luca pointed out to, called discuss.pytorch.org, that already has 13,000 plus posts. And so if you have some problem, You can do some Google search, and hopefully and typically you will like find a lot of posts trying to answer what your question would be. We've had 300 plus fantastic contributors from the open source community who have contributed to PyTorch in various ways. And if you like open source and if you like contributing back, feel free to jump in and send some pull requests. PyTorch was built by people from many places in the world, many universities. This is just a small subset. I just want to thank every one of them, and that's about it. Thank you. So now, Luca?
Yeah, if you have a few questions.
Yeah. Yes. Yeah, if you have questions, feel free. Hi.
Yeah, do you have any plans of releasing a visualization tools or a visualization library for just like embedding images or
Sure. Question is, do you have plans for releasing visualization tools? We're actually planning this now. There's actually many tools that popped up in the community. There's actually one tool called TensorBoard PyTorch that uses TensorFlow's TensorBoard visualization package, but you can use it with PyTorch. There's also another tool that we at Facebook released called Wisdom that in the browser you can have some visualizations going on. That's kind of what we use internally. And we are planning like a much more deeper integration with TensorBoard. So the TensorBoard package now is maintained by a community member, and I think it's not fully feature complete, but I think we'll try to dedicate more time and resources, but we're still planning this out. It'll come over the next few months.
There is any tool like TensorServe for putting in production the model that you produce with PyTorch?
Sure. The question is, if you want to put PyTorch into production, is there any package like TensorFlow's serving package? And yeah, so Python ecosystem is pretty rich. So you can use something like Flask or Tornado, like all of these things you can use to serve PyTorch into production. I know several people who just use a standard simple Flask with the REST API and they just serve it. Because PyTorch is just a Python package, we don't need a separate package that will serve it. We have PyTorch has a package called multiprocessing. Python has a package called multiprocessing, but in PyTorch we forked it to make it much more efficient. So if you want to serve multiple requests at a time, then it's just like a 5-line change to add that. We don't have an official example of how to serve PyTorch models into production, but I think if you're familiar with the Python ecosystem, it's very natural.
Just one other. About the MPI, do you have a plan to integrate with Spark and Yarn engines?
So about the MPI and Spark and Yarn, the answer is no. Typically, Spark is not really suited for deep learning workloads. It's more like, okay, we have this huge problem that's sort of MapReduce, and we want to distribute it over a lot of CPUs because that's kind of how the problem can be effectively solved. But deep learning workloads, like most of these can be solved with like 1 or 2 or 8 GPUs, and if you want to use multiple machines, you typically don't think about using 10,000 CPUs to solve a problem. You think about using 4 machines with maybe 4 GPUs each to solve the problem, and we didn't think it made any sense to do like more traditional big data type integrations.
As someone who comes from a vanilla Lua Torch kind of workloads and having tremendously enjoyed the PyTorch release, is there any future for Lua Torch, or that's to be considered deprecated?
The question is around Lua Torch and around what's the status, is it deprecated? The future of Lua Torch looks pretty bleak. Like All of the people who are developing LuaTorch, they've stopped developing LuaTorch and moved to PyTorch, except maybe one person, I think. So I am still the only one maintaining LuaTorch. I still merge some critical patches and stuff. Truth to be told, I'm basically leaving that as untouched as possible. I don't want to change any small thing that will then take me days to fix. Like, I'm just leaving it in stable maintenance mode. I'm not changing any of the scripts. So if you want to use it for your current project or so, like, nothing will move. But new features, I don't think will come. Yeah, they won't really
Still,
come.
I mean, if I'm not mistaken, PyTorch does use the TH and THC libraries from,
Yeah.
from the core.
PyTorch does use the C libraries of LuaTorch, and they have been updated in the LuaTorch side as well. So if we added some CPU optimizations in PyTorch, and then they automatically came to LuaTorch. But we are, like, as of last week, we are starting to do these only in like 3-month cycles. Like, until last week, we used to do this every commit that came into PyTorch, it would just go to LuaTorch automatically. But with PyTorch adding Windows support and stuff, there's a lot of moving parts. Like, there's a 25,000 line diff that I just merged into PyTorch around Windows support, and that touches a lot of C code. I don't want to push that back to LuaTorch because that's just, I don't know how that will interact with the user's project in LuaTorch, and it's just one of those things. If LuaTorch is in maintenance mode, I don't want to get that back. But if there's any critical optimizations or patches, I will manually keep merging them back.
About exporting model weights, for example, for using, I don't know, I want to use my train model in, for example, an Android application or something. Is there anything?
Yeah. So the question is, I want to, let's, for example, train an Android, train my model and then use it in an Android thing or something. Can I export my model weights, my model structure? There is. We just announced 2, 3, maybe a month ago, we announced a project called Onyx, ONNX. So PyTorch can export its models to this Onyx format, and Onyx can be consumed by Cafe2 and soon CNTK, and we have a community member who did a small TensorFlow support as well. So you can export PyTorch to Onyx, and Onyx can then be, Onyx is just a small protobuf model weights. So then you can even import it into your own backend, for example.
Just a question about CUDA. Since you say core kernels are compiled, do you mean that you can actually use the runtime CUDA, or do you still need the software development environment?
So we don't need anything to be installed from the user side except the NVIDIA driver. Like with the PyTorch binary package, we actually also ship with like some of the CUDA binaries that are needed. Okay.
Good.
Thank you.
Sorry, another question. I know NVIDIA is the leader, but do you have any plans to support OpenCL?
Good question. We are not going to support OpenCL, but that's for very good technical reasons. We did a full evaluation of, using OpenCL and stuff. It's just has fundamental problems. For example, if you have OpenCL with some AMD card, then the AMD driver itself for every launch of an OpenCL kernel will take a millisecond or so, and that's just really slow. Instead, what we're doing is we're collaborating with AMD to support their new API, and we have like preliminary ports of PyTorch using this API. It's called HIP, and once that is ready and stable, we will merge that into master and announce that we also support AMD cards.
Okay, thank you.
Great. Now
I think
we
it's
go
time
with-
to move on.
Yeah.
Thanks, Sumi.